Can you see my screen?
Yeah, we can see your screen, but you're now not yet in a full screen mode.
Just a moment. Okay, can now you see full screen?
Yeah,
okay.
Now it's a full screen and it's perfect. It's your show.
Okay.
Thank you.
Thank you. So hello everyone, I'm Loris Maria Cangemi. I'm a postdoctoral researcher at University of Naples, Federico II, and I will talk about optimal energy conversion in the absence of time reversal symmetry, which is drawn from a work joined with the joint collaboration with some people from Naples and Genova and Como. So here is a brief outline of my talk. I will shortly introduce the context of optimization in quantum heat engines. Then I will shift to two main examples of isothermal heat engines, and I will draw some conclusions at the end. So optimal performance of heat engines have been a modern field of research. Mainly, there have been contrasting claims in literature. For example, in the context of steady-state heat engines, if we put a magnetic field in order to break time reversal symmetry, the second law of thermodynamics by itself does not preclude the achievement of ideal efficiency at finite power. However, other claims regarding Markovian system deny this possibility by bounding the output power from above by the difference between the actual efficiency of the system and the Carnot efficiency, so that if the efficiency tends to the Carnot limit, the output power is bound to vanish. However, if the system, the working fluid, is a quantum many-body system, working near criticality, Carnot efficiency can be approached at actually approached at finite power, but at cost of diverging output power fluctuation. So this kind of machine would be of no use. In order to circumvent these drawbacks and trying to reconcile all these contrasting claims, thermodynamic uncertainty relation were put forward, which holds for machines working under the overdamped Langevin dynamics. And a lower bound is put to the trade-off between entropy production, sigma, and relative output power fluctuation, which is the out over the square of the power, so that if your machine works at close to zero entropy production, your fluctuation, the fluctuation in the power, the output power, tends to diverge. And also, this kind of inequalities was generalized in the context of periodically driven heat engines, steady-state heat engines. Now, the point of our work is this: is it possible to devise a minimum model of quantum engine where the working medium is composed of a single quantum degrees of freedom, achieving near to ideal efficiency, but without sacrificing the output power, so at finite power? The answer is positive, but if the time reversal symmetry in the dynamics of the system is broken. And also, we show that for similar instances of engines, the quantum coherence in the dynamics can lead to violation of thermodynamic uncertainty relation for devices for periodically driven systems. So I will talk about two very simple instances of isothermal heat engines. Here these two instances will differ only by the working substance here, which in the first case, I will take as a linear quantum oscillators, and in the second case, I will take as a two-level system. Both these systems are constantly driven out of equilibrium by means of two different periodic drive. And also, this working substance is permanently put in contact with a thermal reservoir, so that the name isothermal heat engines. So let's start with the first example. The first example of the linear oscillator, we can work out we can write down simply the Hamiltonian of our system, which is a driven quantum harmonic oscillators, where the driving are coupled to the linearly coupled to the position operator and momentum operator. Here we have the two driving fields, epsilon1 and epsilon2, and we model the bath by means of a Caldera-Leggett model, which is a set of infinite set of quantum harmonic oscillators. We define also the spectral density of this bath as customary in Caldera-Leggett model by this sum of delta, this infinite sum of delta. So what is the point? How this machine, how this device can work as a machine? Then we can see that there exists parameter range in this Hamiltonian, where if we provide a given amount of work in input, the system is able to deliver part of this work in output here, and by wasting the difference part of this work in the reservoir, dissipating into the bath. So we will study the performance of this kind of simple kind of isothermal heat engine in the non-equilibrium by exactly solving the non-equilibrium dynamics. So this model is very fine because it's a very well-known model, and it's exactly solvable in the sense that we end up solving a sort of like an equation like this, which is a generalized Langevin equation for the expectation value of the operator, the position operator. Here you may note that the dissipation has memory, so the memory effect is described by the memory kernel here, and the system is only initially in a product state of the system, of the oscillators and the bath in the distant past, in the far past. Also, we take a spectral density in the continuum limit that has this form here. The index S is crucial because it distinguishes between subohmic, ohmic, and superohmic dissipation, and omega C is a cutoff. Is a frequency cutoff, which is the largest energy scale of our system. So it's a continuum limit with a large energy scale. You can work out the solution, which is very nice because it's the exact response to driving field is exact for any field strength, and the linear response is exact. And here we can write down the response function in the Fourier space, and they are written in terms of the damping function, the damping function, which is the Fourier transform of the kernel. So this simplicity of this model allows for get rid of Markovian dynamic and the overdamped limit, and also fast and slow in driving regime can be equally studied, and strong coupling effect can be probed. So now how we write down the work, the total work per cycle. So the total work per cycle would be the standard formulation of work written in terms of partial derivative of the Hamiltonian, and rho here is the state of the total system, and we can also easily associate the work to each channel here. To each channel corresponds to a drive. And the interesting parameter regime will be the one where the mean power per cycle in one channel and in the other would be of opposite sign. So a channel will drain power while the other channel will deliver it. How to evaluate performance? Then we evaluate performance like introducing the efficiency of our engine, and also power fluctuation. The output power fluctuation would be written easily in terms of 2 times autocorrelation function of the powers, and also mean relative fluctuation would be taken by taking the average, simply the average of the period. And we will study this kind of figure of merits. Okay. Okay. Thanks to the analytical form, the response can be recasted in terms of Onsager matrix formalism, which is a very common in steady state heat engines. And here the output power will be the mean output, the average output power will be a quadratic function of the fields weighted with the Onsager matrix. And this formalism, when we choose a form of the fields, of the driving fields, which is the form I write here, with two monochromatic fields of frequency omega, where the phi is the phase difference between this drive. The form of the Onsager matrix will be easily related to the chi function. We can see that this formalism allows us to encode directly the absence of time reversal symmetry in dynamics, because the time reversal symmetry is controlled by this parameter phi, and also optimal operating regimes are directly encoded in our formalism, so that we will work at maximum efficiency point. And I skip at the results of this procedure. Here we plot the efficiency at maximum efficiency, the input and output power of these engines, of this engine, and the relative output power fluctuation. And we will see that when this when the efficiency in the anti-adiabatic limit, which is when the frequency of the drive is it's greater than much more greater than the proper frequency of the oscillator, tend to the ideal value. Here we see that the output power scales linearly with the frequency. And also we see that the relative output power fluctuation not only are finite, but they are vanishing. So we realize that the anti-adiabatic driving regime is very special because it performs this peculiar scaling of the performance indicators, and the scaling for generic S is written here, is reported here. Okay, non-Markovianity in the bath. So if you consider, for example, subohmic and superohmic dissipation affects the power efficiency trade-off according to this scaling law, and we'll see that the efficiency, the optimal efficiency, is approached with different velocities as for various S, for various values of the index S. And based on this this result, we compared our the performance of our machine with the thermodynamic uncertainty relation bounds derived by Seifert and coworker. And thanks to the scaling of this trade-off parameter at maximum efficiency, we see that in this figure, we see that the ratio between the trade-off parameter and the thermodynamic uncertainty relation bound goes to zero, both in the quasi-static limit and in the anti-adiabatic limit, so that we observe violation of thermodynamic uncertainty relation for this kind of device. But our isothermal engine violate this bound, but fulfill the unified thermodynamic uncertainty relation bound, which was derived by Maciejczak and co-workers in the field of linear response and absence of time reversal symmetry. So I can discuss the second part of the talk, which relates to another instance of essentially the same mechanism, but we changed the working substance with a two-level system, which is periodically driven by means of a couple of periodic fields, and but these periodic fields are coupled to the sigma z operator, and we modeled the system as a driven spin boson model, where the bath is again the caldera-legged bath, we see that this, we know that we do not have an analytical solution for this kind of system. So we will rely on numerics. Say, oh, our numerics will be a short iterative length method, which is a method based on exact diagonalization, which allows us to propagate the state, the full state of the system and the bath, which are coupled, and it can be strongly coupled, so that we can see the strong coupling physics of this model beyond any weak coupling approximation, and for nearly all values of driving frequency. Here is an example of the output of of our numerical simulation. You can see here, if we define the power, the output, the power along the two channels in terms of the average, the quantum expectation value of the sigma z operator, we see that we can follow the evolution of this power, and we see that it's you can see the conversion mechanism appearing here, and also the energy balance here, and here the energy scale are in the scale of delta, which is the tunneling amplitude of the two-level system.
Hello. Sorry,
yeah.
Loris, you have 5 minutes.
Okay, I'm closing, and here the Onsager matrix. The Onsager matrix, we can compute the Onsager matrix, and we can compute the Onsager matrix by numerical means, because the linear response regime is not exact. So for sufficiently small driving fields, we can adopt the same strategy regarding the fields, but we can compute numerically the two-time correlation function, the exact two-time correlation function, and compute the Onsager numerically, the Onsager elements numerically. And here are our results for the performance of this engine. We see that we plot the power here, the absolute fluctuation, the efficiency here in C, and in D, the relative output power fluctuation, and we see that we don't have the same scaling as the same fortunate scaling as the previous model, but we see that the power is finite in the antidiabatic limit is finite, but it is vanishing. In some sense, it's vanishing. However, we can monitor the performance of this engine in the when we increase the coupling strength, and you see that you see no Markovian effect, which clearly comes in as came in as the frequency the frequency of the two-level system, the gap of two-level system progressively shrink here, which is a consequence of renormalization. And also you can see that by increasing the coupling with the bath, fluctuation tends to decrease in their peak, but also to increase in the antiadiabatic limit. Obviously efficiency decrease. And so in this system we can study if thermodynamic uncertainty violations are present, and indeed they are present. They are present because we plot the thermodynamic bound, the TOR bound in gray lines, while the colored lines are the trade-off parameter at the maximum efficiency, and we see that when we move from weak coupling, we observe a distinct pattern of violation in the antiadiabatic driving regime, while in the quasi-static limit, the bound is generally obeyed. If we move to strong coupling regime, we see that the violation narrows, the violation range narrows, and here, which is the paradigmatic case of alpha equal to 1/2, when you have complete decoherence, so the dynamics of the system is not coherent anymore, you see that no violation occurs. So we can relate the occurrence of this violation to the quantum coherence of the working substance. So I conclude, and we show the two very simple and miniband models of isothermal heat engines working at with time reversal in the absence of time reversal symmetry, and we showed that their interesting performance and also interesting pattern of violation of thermodynamic uncertainty relations. Thank you for the attention.
Thank you very much for the very nice talk. And let's see if there are any questions. Can I ask a question?
Yes.
Sorry, in your first part of the talk, when you're dealing with harmonic oscillators, you are always, yes. I mean, you have a harmonic oscillator in harmonic bars, which in your model is quadratic. And if I remember correctly, my discussions with Juan Pablo Paz, we always kind of came to the conclusion that it's essentially classical, and all quantumness is sitting inside of the initial conditions of your harmonic oscillator. And have you tried to compare what you do with classical oscillator, which will be driven? And so what is quantum in what you are observing?
Okay, what is quantum is mainly, obviously you are right, what is quantum is mainly in the fluctuations and in the, essentially in the temperature dependence on fluctuation. But yes, you are right. If you look at the means, if you look at the average mean values, they obeys to so they behave as they were classical. And yes, I mean, I would say that if not for the fluctuation, this system can be thought as a classical system. Yes.
Okay, thank you. There is a question from Ashan. So thank you for the very nice talk. Can you please say a bit more about how you go beyond weak coupling limit in the spin engine case? What are the limitations?
Yes. So essentially, I go beyond the weak coupling approximation by employing a fully numerical method. The fully numerical method is based on short iterative lengths method, which was a method we briefly introduced a couple of years ago. We applied actually this method to the spin boson model, and it's based on exact diagonalization and Krylov tree diagonalization at any time of your matrix. Of your state, so you can evolve the entire pure state of the system, and you can then perform the trace over the bath and get to the reduced system dynamics. So you can describe the strong coupling system but coupling limit up to the Toulouse point of the spin boson model, which is the analytical isolated point in the parameter in the phase space. Actually, if you want to go to stronger coupling, I think that you have to rely on transfer networks. But in this case, if you are in this window of coupling strength, you can rely on short iterative lengths. And also, yes, actually, this was taken from the analytical results here, but you can go. Ideally, you can move here numerically.
Okay, thank you. And Tiago have a question, so I allow him to talk. You're welcome to ask a question, Tiago.
Hi. So I have a very simple question. I mean, so your engine actually just only have one bath, no? You're converted to work. You're exactly. Losing some work on this. I mean, what's the motivation? I mean, for this kind of engine?
The motivation in the sense that is it useful at all? This is a.
I usually think of an engine that's converting heat to work. So I mean, the usual scenario.
You can think on the calorimetric experiments, and you can think on thermoelectric device. In the end, this is This is a simple, very easy, very minimal model of a thermoelectric device. So when you replace the two fields with two terminal of a device, so this is from this point of view, it's a standard thermoelectric device.
Okay, I see, I see.
Okay, and I think also Marty have a question. Marty, you're welcome to ask your question.
Yes, thank you. Thanks for the nice talk. So I was wondering, okay, good in this slide about this anti-adiabatic regime, because if I think about it, as you go faster and faster, at the end you tend to a quench. And I would expect that in this quench you have efficiency 1, finite power, and basically fluctuations will be the ones coming from the quench. So is this what you are getting, or it's a finite time correction to this?
No, actually, you are tending to that limit, but the system and so the bath oscillators are not frozen, because they can respond at every frequency. So I anticipated here that maybe it's confusing, but I anticipated that we take a continuum limit, and the cutoff frequency of the bath is the largest energy scale. So if you go to very high frequency, but you have to consider that your bath can respond even to larger frequency. So the minimal time scale, it's the inverse of the cutoff frequency. So the bath oscillators are not frozen; they are responding, and the system is exchanging power with it's continually exchanging power with the bath, and the energy of the bath diverge in this sense.
No, but okay, maybe sorry if I didn't follow you, but I don't mean that I go to a very large frequency, but I can go, I mean, I can only change the frequency a bit, but I do it so fast that the bath doesn't have time to respond.
No, it's not true, because the bath, it's the frequency of the bath is the cutoff frequency is it's at infinity. It's infinite. It's not true. The bath responds. Okay.
Okay, thanks.
Okay. Do we have any more questions? Okay. Even if the people have any more questions, because I don't see right now, but I'm sure somebody will come up with a question, they can always address you via email. Okay. And we could probably wrap up this session. I thank all the speakers of this session, because it was very nice and very interesting and informative session. And I think Camille can tell us what still waits us today. Thank you.